Okay, back to this from the beginning. All right, I think we're actually ready to get started. What? I think so. You can hear me, right, Tamika?
Yeah, do you usually share the PowerPoint or no?
Okay, I can hear you too. That's good. All right, and we do have a guest joining remotely today. Okay, so I have to remember to like stay close to the mic. Hey, how are you? Tamika can't see what I'm doing, but I'm being very showy with my mic.
Can you share the PowerPoint when you get a chance?
Can I what?
Can you share the PowerPoint when you get a chance, or do you not usually?
I think, Tamika, that I added you as a guest to the Husky CT site.
Oh, okay.
So I think you should be able to get everything, which includes a PDF of the PowerPoint.
Okay, thank you.
You're welcome. I figured, why not?
I appreciate it.
And tell me if guest access doesn't get you enough and I can change you to student, but I didn't want to confuse things. So I used guest. There was guest, there was visitor. I don't know what all the differences are for those kinds of things. All right, cool. So here we go. Week 4. Can you believe it's week 4 already? We're like almost a third of the way through the semester after today. I say that you haven't had a class with me. Anybody who's had class with me before knows that I count down the weeks because I get really stressed out that we have so much to do and so little time. Yeah, so I'm like, oh my gosh, it's week 4. I mean, I can't believe it. This semester is going fast. And we are already behind. I don't know how that happened. So I'm contemplating how we'll make it work by the end of the semester. But so the plan, so we still need to talk more about CFA and measurement models because we didn't finish that last week. We definitely need to talk about, it's okay, I can't see it. We need to talk about hybrid models. So how do we put together measurement models and structural models to actually fit a full hybrid SEM? And then we need to talk about measures and model fit. So that's a very ambitious agenda for today. Here's my fallback plan. If we don't get to measure, I think we will certainly get through measurement models and hybrid models. There is a possibility we won't get through or to the measures of model fit stuff, which is at the end of the PowerPoint. If that's the case, number 7 on the homework is the only one that's about model fit. And so you'll just do numbers 1 through 6 this week and not number 7. So I got a plan so that we don't have to feel totally rushed to get through everything today. But we'll see how it goes. Having said that, we still have, even without the measures of model fit, we have a decent amount of stuff to cover. So with that said, let's go ahead and get started. And I feel like I want to just do a quick review of some of the CFA stuff that we talked about a couple of weeks ago, because remember, we started talking about CFA in week 2, then we put it aside last week to talk about fitting path models and to do our little intro to M+. So I want to start by just doing a very brief review of some of the things that we said in week 2 about confirmatory factor analysis. And then we'll move on to, and then we have some more things we need to say about measurement models and confirmatory factor analysis. And then from there, we will move on to talking about how we actually put measurement and structural models together. Okay, so again, this slide should totally be a review. I know we looked at it a couple of weeks ago, but remember, and this is always going to be the case, to scale, when we have a measurement model, a confirmatory factor analysis model, or a measurement model of any kind, to scale the latent variable, we're either going to have to fix the factor variance to 1 for each of the factors, or we're going to have to fix the loading of one of the indicators to be 1. So we're going to do, and actually technically there are other things you could do too to make a constraint. Like there's I'm not going to talk about this in any detail, but there's actually kind of an effect coding strategy where you can sort of like constrain the mean of all of the loadings to be 1 or something like that. We're not going to get into that, but you could do something like that. But you've got to make one constraint. However you do it, you've got to make a constraint. Now, why would you choose one versus another? for standard CFA models, it's not going to matter too much what you choose. When we get into multiple group confirmatory factor analysis, it is going to matter, and you're going to want to use something like a marker variable strategy in that case. You're not going to want to fix the factor variances because, you know, you might be interested, for example, in whether the two groups differ in terms of the variant, you know, their variances on this factor, right? And so if you have a multiple group situation and you fix the factor variance to 1 in both groups, then you can't get a sense of, you know, for example, is there more variability for males or females in terms of motivation? I'm just making something up here. Again, I'll talk about a couple strategies when we get into multiple groups to deal with that. But it's in the multiple groups scenario that it's often becomes really useful to use the marker variable strategy. And, you know, just in general, I think the marker variable strategy is the default for most programs. And if you use the marker variable strategy, you're going to get standardized and unstandardized parameter estimates. So I don't know. I mean, we'll tend to use the marker variable strategy, but in some cases, it really doesn't matter too much. So how do we decide, and this is not something we talked about before, but how do we decide what variable we should use as a marker variable? Any thoughts? Yeah.
If it's in like a metric that you want.
Yeah, so the first thing is you want the marker variable is actually scaling the latent variable. So the latent variable scale is going to be in the metric of the marker variable. So, you know, now all of your variables might be in the same metric. That's possible. But if they're in different metrics, or, you know, you want to think about using the marker variable that maybe sort of you feel like best represents the latent variable in terms of the metric. The other thing is you want the marker variable to be a good indicator for the latent variable. Because what if it turns out, let's say, that you pick a marker variable that is, well, worst case scenario, if you pick a marker variable that's completely uncorrelated with the latent variable, then that's actually, that model is going to end up being what's called empirically under-identified, right? So if for some reason you had an indicator and you said, okay, I want to scale the marker variable to this indicator, and then there's absolutely no direct path there, there's no relationship between the indicator and the marker variable, but then you haven't scaled the latent variable, the model is going to be under-identified and things are going to go haywire. I call this empirical under-identification because, you know, empirical under-identification means, hey, if I drew out the model, right, before I collect data, if I looked at this model, it would look like it's identified. But once I collect my data and I try to fit the model, it's actually not identified because of the pattern of correlations or covariances in my data. And I'll give some examples as we go along of where we might hit empirical under-identification problems. Hannah, yeah.
Yeah, so does that mean that if all of your indicator variables that are loading on your latent variable, if they're all in the same measurement unit, can you just see how they all load and then pick the highest one? Like,
well, you know, you said, can you see how they all load and pick the highest one? But
if you don't have like a theoretical background.
Yeah, I mean, yeah, theoretically, except for how are you going to get those parameters? How are you going to know which one's the highest loading? Like, you're going to have to start with something, right?
Oh, do you have to have something fixed before you?
Yeah.
Oh,
we have to do this.
Have to have the measurement.
Yeah, we have to do this right off the bat. So I mean, theoretically, that would work, except for that if you pick the wrong.
Set each to one.
Well, so you know, the reality is it's not going to matter too much as long as you don't pick a total dog of an indicator. So you don't have to have the best indicator be the marker variable. And, you know, if all of them are reasonably good indicators, even the worst variable could be an okay marker variable. When things are going to be problematic is if you pick a marker variable that really literally doesn't belong on that factor. So usually we can do that a priori. We can use their sort of piggyback on what you were saying, but just change it a little bit. One thing is I can look at the pattern of correlations among the observed variables there, right? And obviously, you know, if there's one variable that seems to be pretty well correlated with the rest of the variables, that's going to be a fine marker variable, right? So I could do it empirically. The other thing I could do is just look at the items or the subscales and say, okay, which of these things do I conceptually think is the most representative of my factor, and that has two advantages, I think. Advantage one is should work well, and advantage two is, and again, this sort of assumes that everything's in the same metric, right? So there isn't a reason to pick something different. But reason two is, it just kind of makes sense to kind of yoke the latent variable to the indicator that you feel is best representative of the latent variable. So you don't have to stress really about what the marker variable is, as long as you just don't pick something that's really, really bad. Does that make sense? Okay. All right. And I probably got ahead of myself. I think I got a slide on that later on that will just fly by, but good to say. All right. So again, this is just sort of showing what we're talking about for the different parts of the confirmatory factor analysis, right? We've got in the unstandardized case, it's actually going to be covariance among the factors, but in the standardized case, it'll be a factor correlation. The pattern coefficients are those paths from the factor to the indicator variable. Usually in confirmatory factor analysis, even if you use a marker variable, people will usually report the standardized path coefficients or the standardized pattern coefficients. I mean, they're paths, right? But they're often in measurement models called pattern coefficients. They're also sometimes called factor loadings. That's kind of a colloquial term for the pattern coefficient. Some people don't like that term because it has a little bit of an ambiguous meaning, but I think it's probably the most common thing that people use. And then, obviously we have errors. We have measurement errors for each of our observed variables. And remember, our observed variables here are endogenous. The only exogenous variables here in this model are actually latent, the way that it's drawn, right? So we have two latent exogenous variables. Those are correlated with each other. And then we have these endogenous variables. And remember that we could allow the errors of two. I mean, again, we want to think about whether we want to do this or not. Conceptually, it might not be something you want to do, but we can allow for the errors of two of the variables to be correlated with each other. And that means that the covariance between those two indicators is either higher than would be predicted by the factor structure. If the correlated error is positive, it means that those two items or indicators are more related to each other than would be predicted by the factor structure and sort of the rest of the factor structure, right? Or, well, the factor structure, because the correlated error is a part of the factor structure. Yeah?
Are you changing the slides?
Did it not change at all for you?
No.
I did. Huh. I wonder why that happened.
Sorry.
No, that's good to know. I'm only one slide up, but why did it not change? Okay, let's see.
I can see it now. Are you on 3?
Yeah, but why did it? Okay, well, so let me just hit from current slide and then tell me if it doesn't change the next time I change. You can see it now though, right?
Yeah, thank you.
Sure. Okay, if the correlated error, if that correlation is negative, which happens a lot less frequently, by the way, that actually means that those two indicators are less related to each other than would be predicted by the factor structure. So most commonly we'll see positive correlated errors, but you could see negative correlated errors. But really what the need for correlated errors is telling you that the factor structure is not adequately reproducing the correlation or the covariance between those two indicators. Yes?
I think I'm just trying to make sure that I got this right because I also had this question based on the homework. So for indicators, you don't necessarily correlate the indicators themselves, you're correlating their errors because any other variance is going to the latent.
Yeah, that's right. Notice that we're correlating the errors. And remember, if we have an endogenous variable, whether it's in a measurement model, so it's an indicator, or whether it's in a path model, so it's just like an endogenous variable, we're not estimating the total variance. We're always estimating some sort of residual variance. So we can't directly correlate those two indicators because they're endogenous. All we can do, is actually allow the unexplained part of those two variables, the residual, which is in this case measurement error, because we're in a measurement model, we can allow those to be correlated. Because remember, for any endogenous variable, the total variance isn't a parameter in the model, right? So the variance in BSI2, for example, is predicted by, there are two pieces, right? One piece is the piece of the variance that's predicted by the negative affect factor. And the other piece, that E2, is just the variance in BSI2 that's not predicted by negative affect, right? So that's, we basically, for every endogenous variable, we're chunking out variance explained, and it could be explained from multiple sources. And then there's the unexplained variance. And when we correlate the errors like that, then we're saying, hey, the unexplained variance in BSI2 is related to the unexplained variance in BSI5. And if you think about what that means conceptually, then that means that, okay, like the negative affect factor, it had first crack at explaining variance. Oh, well, in this case, it's not the negative affect factor because they're on two different factors. But the negative affect factor had first crack at explaining the variance in BSI2, right? And the hopelessness factor is explaining variance in BSI5. And then the piece of BSI5 that isn't explained by hopelessness, and the piece of negative affect that isn't explained the piece of BSI2 that isn't explained by negative affect, those two residual pieces are correlated with each other. There's something else that we could do. It's different. I'm not saying this is the same as a correlated error, but another way that you could modify this would be to say, can you see that, by the way? Did you see me drawing, Tamika?
No, but that's okay.
Okay, sorry. I just put a path from hopelessness to BSI2. If I put, now BSI2 is double loaded, right? So now that changes. Think about it. If I do that, that changes what E2 is now. The residual variance in BSI2 is now the variance in BSI2 that isn't explained by negative affect or by hopelessness, right? Because now there's a direct path. Before, the residual variance was really just the variance that wasn't explained by negative affect. But now it's the variance that's not explained by either of the two factors. So that's another way that we can make model modifications, is to allow indicators to double load on multiple factors. That's not, by the same way, the same thing as correlating the errors, right? And you could do both. So the model that I've drawn here, where we have BSI2 double loading, and then we have a correlated error between BSI2 and BSI5, that's still, that's still like a model that we can fit. Again, I go back to, like, conceptually, does that make sense? That's what you need to ask yourself with your own data. Just because you can double load a bunch of things and you can have a bunch of correlated errors, does that actually make sense? Should you do all this stuff willy-nilly without a theory? Absolutely, absolutely not. But in terms of like the rules of, specifying these models, you can have double loadings, you can have correlated errors. Where we will run into potential problems fitting measurement models, though, is if we have a lot of double loadings and a lot of correlated errors. So those standard CFA models we talked about will generally run like a charm, unless there's something weird, like you've got an indicator that uses a marker variable and it's not related to your factor. But if you have a lot of double loadings and or a lot of correlated errors, or both, those are the kinds of models that will sometimes cause us problems. And later in the semester, when we talk about multi-trait, multi-method matrices, which are a specific type of CFA model where every item is actually double loaded on a trait factor and a method factor, they're super cool models, but those are models that often do have convergence problems or empirical under-identification problems. Yes, Claudia.
Can you repeat again your vocalized factor correlation? How do you explain it again?
Oh, the correlated error. What does the correlated error mean? Is that what you're asking?
No, for the factor correlation.
What does the factor correlation mean?
Yeah, if you can repeat what you said.
Sure. So the correlation between the two factors, I mean, that's just how correlated are those two latent variables, right? I mean, it's, in the unstandardized metric, it's going to be a covariance. And when you look at the standardized solution, it's going to be a correlation. So generally speaking, when we go to interpret those, we're going to look at the standardized solution because it's a lot easier to interpret correlations than it is to interpret covariances,
You
right?
said something about the indicators. That is the correlation that the indicators cannot predict, or
What I was saying is, I don't think it had anything to do with the factor correlation, but what I was saying is, when you pick the thing about marker variables, or
I don't know, something as like the factor correlation is the information that the indicators themselves cannot identify within the factors. So that was
correlated.
not.
That's
That was
correlated
right.
error.
That was my.
yeah, the correlated errors is what I was
okay.
talking more about, right? So remember that the errors are always residual variance. I think that's the really important point. And Hannah was asking, well, can you just correlate the items with each other? Only if they're exogenous. I think that's the thing to remember. If you want to correlate two variables with each other, they need to be exogenous. If they're endogenous, you can't directly correlate the variables. You're correlating their residuals, which in a measurement model, we call those residuals measurement errors. In the structural model, we call those residuals disturbances. But either way, if a variable is endogenous and you want to correlate it with something else, you can't. You have to correlate the residual, right? You can't directly correlate the variable. You correlate the residual. Yeah.
And because M plus knows which ones are exogenous, if you put the width of the exogenous, it will automatically do the disturbances.
That's right. And M plus is smart. Very, very smart, and has lots of built-in defaults, which you'll come to love later on because they make it really easy to write code with just a few lines. But in the beginning, and actually this was one of the things that I was most worried about when I switched from teaching in Amos to teaching in M+, because I was like, oh my gosh, they're going to get so confused. Because when you say BSI2, if it's an exogenous variable, that means BSI2. And when it's an endogenous variable and you just say BSI2 in the code, like all by itself, right? That means the residual of BSI2, the measurement error or the disturbance. So you're absolutely right. M+ is smart enough to know whether it's exogenous or endogenous. And if it's endogenous, calling the variable really means you're talking about the residual of the variable. But like for you, because you're just getting started, you might not realize that M+ is that smart. So to you, it might look like you're literally correlating two variables when in fact, what you're doing is correlating the residuals of the two variables. And this is where actually having M+, even though they're ugly, but having M+ spit out those diagrams from the model can be helpful for you when you're first getting started. Because you've written the code, you run the model, and then you can look at that ugly, graph of the path diagram graph that M+ spits out. And there it will show the errors, and it'll show that the errors are correlated and not that the variables are correlated. So if you're unsure, that can be something that you can kind of use to get your bearings. But that's absolutely right. Yes.
So for me, it makes sense that why endogenous variables of the same factor cannot be correlated with each other, but I'm wondering.
I never said that. I never said that endogenous
you
variables
didn't-
on the same factor
you
can't be
didn't say
correlated.
that.
They
It's
can.
logic that because they are loading on the same factor, so there shouldn't be any correlation between themselves.
Okay, so I agree with what the last part. When you said, hey, they're on the same factor, right? So theoretically, I shouldn't need a correlated error. Yes, I totally agree. Conceptually, that makes sense. But there's nothing that says that two variables on the same factor can't be correlated with each other. And what does that mean? Again, if I have two variables that load on the same factor, and I build in that correlated error, a correlated error between these two indicators, it means that the correlation between these two indicators is not well explained by their joint sort of correlations with or prediction by the factor. So, I think I gave a couple of examples a couple weeks ago, but I'll give an example again. So let's say I have two items on a scale and they're both negatively worded and all of the other items are positively worded, right? So all of these items are indicators of this latent factor, but maybe the two negatively worded items that use the word not end up being more correlated with each other because they're negatively worded than would be predicted by just their relationship with the latent factor. Because, and anytime you have a correlated error, you can think of that as unmodeled multidimensionality. So yeah, you shouldn't need it, right? If I'm trying to build a nice unidimensional model, then I don't want to have any correlated errors. But that doesn't mean that it can't happen. It's a sign of a problem if you were hoping that you didn't need them, but it can absolutely happen. Or sometimes if you use the same wording in two different items, or I mean, it just means these two indicators, yeah, okay, they're both predicted by the factor, but the piece that isn't predicted by the factor here and the piece that isn't predicted by the factor of this item, those two residual pieces are still correlated with each other. So these two items or these two indicators, they share something in common besides what they share with the factor. That's all it really means. So again, like when you're trying to design instruments and things like that, this is absolutely something you don't want to have happen. But, you know, it does happen, right? I mean, it absolutely can happen. And that's what it means. It means that the unexplained pieces are related to each other. Which, you know, again, if you, okay, just one step back. When you run an exploratory factor analysis, how many people have done exploratory factor analysis? Okay. When you run an exploratory factor analysis, you make the assumption, I mean, you actually do have uniquenesses, right? In EFA, when we talk about uniquenesses, those are the measurement errors. And in EFA, when you run an EFA, you make the assumption that none of those errors are correlated with each other. So like standard EFA, you don't have the ability to actually correlate errors for different items. So that's it's a big, and the assumption is that you actually have sort of that the factors explain the dimensionality in the set of indicators. And so that means that after controlling for the factors, all the partial correlations among the items should drop to zero, or indicators, right? And if you're meeting that assumption strictly, then you should not actually need these correlated errors, but you don't actually, often you don't need that assumption. So I'm not saying correlated errors are necessarily conceptually good, but they do tell you something very important. They tell you that these two items are more related than would be predicted by the factor structure that you have posited. And it could be, by the way, going back to my little double loading, it could be, again, a double loading is not the same thing as a correlated error, but it could be that when I allow BSI2 to double load on hopelessness, maybe that helps to fix the problem, right? I mean, there are sort of two ways to fix these problems about multidimensionality. One is to directly say, hey, BSI2 isn't just a measure of negative affect, it's also a measure of hopelessness. And the other way is to say, BSI2 and BSI5, they're just related to each other in some way that isn't captured by my current factor structure. So those are sort of two ways that we can modify confirmatory factor analysis models. All right. So yes, I just talked about this. And again, normally a standard CFA is going to have each variable loading on only one latent factor in the model. That's what's called simple structure. And again, if you think back to EFA, your goal was always that you'd have a simple structure in EFA is you have a large loading on one of the factors and very low loadings on all of the other factors. But here in CFA, oh, by the way, did you see me change the slide, Tamika?
No.
Oh, that's bad.
Sorry if it's a hassle.
That's okay. Maybe I'll just go to, okay. All right, here we go.
Are you on 4?
That's going to be a pain, but okay, here we go. Now you can see it, right?
Yeah, sorry.
That's okay. So now I totally lost what I was going to say though. Oh, yeah, in EFA, you actually are allowing for loadings on all of the other factors. Like if you have a 3-factor model in an exploratory factor analysis, even though you're hoping that this item loads on factor 1, you actually are allowing every item to load on every factor that you extract. But in CFA, that's not true. Remember, if I don't have a direct path going from a factor to an indicator, then I'm saying that the direct effect from that factor to that indicator is 0. So a confirmatory factor analysis is a much more stringent test of the factor structure than an exploratory factor analysis is. It's also way more flexible because we can have correlated errors. We can have double loadings in some places, but not other places. Oh, hold on. Okay, here we go. So maybe I'll just stay out here. You guys can see it, right?
Yeah.
Okay. So residuals, yeah, we already said that. Residuals in CFA are called measurement errors, right? And I think I mentioned this last week, that there's a huge advantage in hybrid models, as we'll see soon, that we can separate out the measurement error from disturbance variance. Okay. So this is just a picture that shows the difference between measurement errors and disturbances. So if you look at academic persistence, that mediator variable, notice that each of the variables that is an indicator of academic persistence has its own little measurement error. But then also notice academic persistence is an endogenous variable, and so it also has a disturbance. And I think if you really kind of like zoom in on that and think about that for a minute, and sort of contrast that to the academic achievement variable, where notice academic achievement is just one observed variable. So that disturbance variance is a combination of measurement error and unexplained variance from variance that can't be explained by academic persistence and growth mindset, right? Whereas if you look at the academic persistence variable, you'll notice that the measurement error part is really captured in the errors for those y variables, right? Because we're saying each y variable can be explained by the factor, and like there's some piece that can be explained by the factor and some piece that can't be. And so we've really kind of captured over here in these errors. Oops. Oh, I didn't mean to do that. That's interesting. Okay. I really kind of captured the errors up here. That's the measurement error. And so the disturbance there, D1, that disturbance is really just the piece of the latent variable, which is measured without error because it's latent, right? It's the variance in the latent variable that can't be explained by growth mindset. So there, I really can partition error variance. Like I've got the variance in academic persistence that's not explained by growth mindset. And then I've got the variance in the 3 indicator variables that isn't explained by academic persistence. Does everybody see that? And that's really, really helpful. And so this is one of the reasons that when we use latent variable modeling, we actually get better estimates of paths and correlations among our latent variables, because those estimates that we're getting are free of measurement error, because we're sort of capturing the measurement error in the measurement part of the model, right? And then when I look at the path from growth mindset to academic persistence, that's actually going to be the direct effect of the growth mindset latent variable on the academic persistence latent variable. So if I were to just collapse these into 2 observed variables and run this as a path model, I would not get the same path coefficient there. It'll generally be lower because the measurement error is baked in, right? So I can't get a stronger correlation than that. Sort of puts an upper cap on the amount of correlation. So you've probably heard people talk about correlations that are attenuated because of measurement error, right? So if I take the correlation between 2 tests, let's say I have a correlation between, I don't know, math test and a reading test, and the correlation between the math and reading test are like 0.7, but maybe the reliabilities of the 2 tests are 0.8, let's say, right? You're looking at the correlation between these 2 tests, both of which are measured with error. But if I have a latent variable, so math achievement, and a latent variable for reading achievement, and I can sort of, right, so now the latent variables are really like the true scores for math and the true scores for reading. the correlation between the two latent variables is going to be higher than the correlation between the two observed variables because the measurement error is just baked in there. Does that make sense? So huge advantage of latent variable modeling. Okay. Okay, so we talked about this.
Can you say that again? The error, the correlation would be higher in the measurement or
The
in
correlation
is it
between
in the
two,
test
if you
or
have,
in the latent?
yeah, no, the correlation will be higher for the two latent variables because those latent variables are measured, you know, those are like the true scores, right? So the true scores are, you know, think about it that way, right? You want to measure, you know, you want to measure creativity and you want to measure motivation. If you have a really bad, so you have a really bad measure of creativity, let's say it's very unreliable, very inconsistent, and you know, and then you try to correlate it with other things because that variable is actually, you know, there's a lot of error in that, right? That's sort of, you can't separate it out. It's all baked in. It's not going to correlate very well with other things, right? In the most extreme situation, imagine if you had a reliability of 0. So all of the variance is error variance. Then you wouldn't expect to be able to correlate that variable with anything else, right? So the degree to which there's error baked in actually attenuates, brings down the correlation between that variable and other variables. But here, we're not correlating two observed variables, we're correlating latent variables. So, right, I've captured the fact that each of these indicators is measured with error, and then the latent variable really represents the true score. It's the true variance in that latent variable. And so the correlation between two latent variables is going to be higher than the correlation between two observed variables. Yeah? Now this can, well, I won't say anything about that. Okay, we'll get to that later. So we know how to count. I think we're good on counting knowns and counting unknowns, right? We'll just practice really quickly. We've got 7 items on this scale. So the knowns are easy. The number of knowns is just the number of unique elements of the variance covariance matrix. So it's going to be 7 times 8 divided by 2, which is 28. Right? We use that same that formula there. The number of variables times the number of variables plus 1 divided by 2. So that's easy. The number of knowns, remember, I need to count. I'm either going to use the marker variable strategy or I'm going to use the fixed factor variance strategy. It doesn't matter when you're counting, you're going to get the same number either way. But if I count the variance of the latent variable, then that means that one of the paths is going to be fixed to be 1. So here I've said I'm estimating 1 variance for the latent factor. I'm estimating 6 factor loadings, not 7, right? The 7th one is my marker variable, so that is not freely estimated. But I am estimating 7 variances, 7 error variances. So I get 6 plus 7 plus 1 is 14. If you want to count with the fixed factor variance strategy, if that seems easier to you, that's fine too. It's going to give you the same thing. You're going to say, okay, I'm not going to count the variance of the factor because I'm assuming it's fixed to be 1. I'm going to estimate 7 factor loadings and 7 error variances, and I'm still going to get 15. But you do need to make sure that when you're counting for every latent variable, you're either constraining a factor variance, the factor variance, or you're constraining one of the paths, one of the factor loadings. Yes?
In terms of the symbols, didn't you say that the variance of the latent factor is a little double-headed, like rounded?
Yeah. So sometimes people will put a little double-headed arrow for the variance, and sometimes people don't on path diagrams. I would say that's not universally used. So if you see it, that's a good indicator that there is, right? That's sort of telling you about the variance of the factor. But don't assume just because you don't see that means, you know, that the variance is not in the model, because I would say that is not universally used in path diagrams. It's what's called RAM notation, and so some people do use it, and it's nice, but I would say more commonly it's left out. Okay, so obviously here we have plenty of degrees of freedom, right? Because we've got 14 degrees of freedom because we've got 28 knowns, we've got 14 unknowns, so we have 14 degrees of freedom here. So so this model is over-identified. So theoretically, I could build in, I could have correlated errors here, right? And each correlated error that I put in would decrease the degrees of freedom by 1. I wouldn't necessarily want to put in 14 correlated errors, though. That would be a bad idea, right? Okay. All right. So in terms of identification for factor model, if you have a single factor model, it's really easy. You got to have a minimum of 3 indicators in order to be identified with a single factor model. And if you count it out, you'll see that if you have 3 indicators in a single factor model, you end up with 0 degrees of freedom. Otherwise, you would have to impose additional constraints. So sometimes when people have only 2 indicators on a factor and it's a single factor model, that's not much of a factor, is it? So like theoretically, that's a pretty lame factor. But if you wanted to fit a single factor model with 2 indicators, you could do it. But what you would have to do is actually constrain the 2 factor loadings to be equal to each other. And by doing that, you would actually be able, you'd be just identified, you'd be able to actually fit that model. It's not, I mean, stop and think about that after class. And what you'll realize is that all you've done is just basically taken one correlation between 2 items and like broken it up into, 2 paths that actually have to be the same. So it's just smoke and mirrors. It doesn't actually give you anything. Like you may as well just say these two indicators are correlated with each other. But I mean, again, it is a trick that people use sometimes. So when I say you must impose additional constraints, that's what I'm talking about. So single factor model, we need 3 items to be, or 3 indicators to be identified. With 4 more indicators in a single factor model, assuming we don't have a bunch of correlated errors, we're over-identified, and so we can actually determine model fit. So we'll actually get a chi-square and degrees of freedom, which is nice, right? Because with a just identified model, you can't actually evaluate model fit. All right, so yeah.
It's over-identified. You mean we can still run the model with having an over-identified model?
Oh yeah, most of our models are going to be over-identified. So remember, this model, for example, is over-identified. It has any model that has positive degrees of freedom, right? We'll say is over-identified.
Oh,
Yeah.
That's
Yeah, over-identified is actually good. Under-identified is bad. Okay, so let's think a little bit though about sort of over-identification for a second here. So here, oops, hold on, I went too far. So here I've got like a just identified model. So there are 3 observed variables, right, that are predicted by this latent variable. And if I wanted to figure out actually what the estimated loading is for the first variable, let's assume that we're just in like a standardized metric, so we're dealing with correlations and things here. That makes it a lot easier. So if I wanted to figure out what the standardized loading is for the first item, it's actually just and this kind of goes back to, you can think back to regression, right? How do you get a regression path, right? Okay, it's the correlation of 1 and 2, the first and second variable, times the correlation of the first and third variables, divided by the correlation of the second and third variable. So if you have, so I don't know if does this sound familiar from regression? It should look familiar to you. So really this lambda 1 is just like a regression coefficient. It's just like a standardized regression coefficient. And we take the square root of that, and that gives us actually the standardized regression coefficient, or in this case, it's really like our pattern coefficient, right? So that's fine, and it's just identified. There's only one solution. We have 3 correlations, we get 1 solution, right? But now, what about if I've got 4 correlations and I want to estimate lambda 1? Well, now there are, like, if you think about it, there's sort of 3 ways I could get there, right? I could say, oh, okay, that path is like the correlation between 1 and 2 times the correlation between 1 and 3 divided by the correlation between 2 and 3, take the square root, right? Or the correlation between 1 and 3 times the correlation between 1 and 4 divided by the correlation between 3 and 4. Take the square root of that. That should also give me an estimate of that path. Or the correlation between 1 and 2 times the correlation between 1 and 4 divided by the correlation between 2 and 4. That should also give me an estimate of that factor loading, of that path, of that regression coefficient. But wait a minute. Are all three of those things going to give me the same answer? Not necessarily, right? And this is what we mean by over-identified. So like, there's not just one way to get the solution, right? Under-identified means there aren't any ways to get the solution. That's bad. Just identified means I can perfectly reproduce my variance covariance matrix or my correlation matrix with the coefficients that I have in my model, because there's only one way to get that solution, which is what I was showing here, right? There's only one way to get lambda 1 here. So I get lambda 1, I get lambda 2, I get lambda 3. I take those lambdas, I plug them back in, I'm going to get the correlations I started with. Like, it's just identified, just like a little algebra problem, right? But now I get here, and with 4 correlations, there are actually 3 different ways to get an estimate of lambda 1. So I'm over-identified. And this is why when I take my parameter estimates, I'm not necessarily going to be able to perfectly reproduce the variance covariance matrix anymore. Because I've had to come up with some compromise estimate of lambda 1 that comes, that has to simultaneously come as close as possible to sort of fitting these 3 criteria. Does that make sense? Yeah. And so that's what over-identification is all about. And that's why when we have an over-identified model, it's like a more stringent test, right? Because no matter, if I only have 3 indicators, no matter what, it's always going to fit, right? But when I have 4 indicators, maybe what I come up with for my lambda 1, lambda 2, lambda 3, lambda 4, when I plug those back in, that model implied correlation matrix doesn't actually look, it may look very close to the actual correlation matrix, or it may look less close. And that's really what we're getting at when we're looking at these measures of model fit.
On the homework, we noticed, we're talking in TA yesterday, that you gave us correlation table, right, to put into into M+, but the sample statistic correlation didn't match, like in the output. No.
But that wasn't a correlation matrix. Yeah. So that's something different. That's because those were the sample statistics. So somebody asked me about this yesterday in an email. So when you plug in to M+ for your homework, remember, you've got means, standard deviations, and a correlation matrix. You plug that all into M+, and if you ask for sample statistics, the first thing that comes back out is what? It's not a correlation matrix. What is it? It's a covariance matrix. So the first thing that M+ does is, again, M+ is smart, and it saves you the trouble of having to do this yourself. But if you wanted to, you could literally take those standard deviations and you could turn them into variances, right? They're standard deviations, so you can square them and turn them into variances, and then you could actually create a variance covariance matrix out of the standard deviations and the correlations. And that's what M+ is doing. And so what it reports out in the sample statistics is a variance covariance matrix that you could very easily, if you wanted to, I'm not suggesting you need to, but you could sit down by hand and actually reproduce that variance covariance matrix, because it's just going from the standardized to the unstandardized. And so that's why that looks so different. But later on, when you fit a model and you get a residual variance covariance matrix, when you fit a model, then you can get a model implied variance covariance matrix. And the residual covariance matrix, the unstandardized residual covariance matrix, is literally the difference between the variances and covariances and the model implied variances and covariances. So that is what your residuals are going to be. It's the difference between the ones you start out with, right? You're actually like your variances and covariances, and the model, the variances and covariances that are implied by the model. All right. So again, with 4 correlations, there are multiple solutions, and we have to come up with one factor loading here that simultaneously provides the best fit for these multiple equations. So like we want to come up with something that comes the closest to simultaneously satisfying all of these equations. All right, so identification for multiple factor models is a little bit, well, it's a little bit more complicated, not that much more complicated. It's super easy if you don't have any double loaded variables or any correlated errors. If you have a multiple factor model and you don't have double loaded variables and you don't have any correlated errors, then you just need at least 2 indicators per factor instead of 3. And the reason is that you can kind of, what you're doing is sort of conceptually, you're like borrowing information from the other factor. And, you know, so you sort of, right, I said with a single factor model, you sort of need 3 legs. You need these 3, you know, these 3 indicators. But if with a multiple factor model, if you have 2 indicators, the 3rd leg is actually the correlation with the other factor. So you sort of still have these 3 pieces of information that you can use to identify that factor. What this means, by the way, is that if you try to run a model where there are 2 indicators per factor, let's say 2 factors and there are 2 indicators per factor, and the correlation between the factors is actually 0, that model won't run. That'll be empirically under-identified. So again, I could draw a picture and say this, theoretically, this looks like it's identified, but as soon as the correlation drops to 0, it's like you have 2 little single factor models, each of which only has 2 items. And so now you're actually no longer identified. So as long as the factors are correlated with each other, you can get away with 2 indicators per factor. I'm not suggesting that's a good model, by the way. That's a pretty lame, that's a pretty paltry way to actually, you know, think of this from like a construct validity standpoint, right? Can you really, I mean, are you really sort of capturing this, you know, robust and interesting latent variable with 2 indicators? Maybe not, right? So I'm not saying 2 is a great number. I'm just saying 2 is the minimum. Generally speaking, though, you'll see people recommend, even with multi-factor models, better to have 3 or more indicators. Okay, so what about these correlated errors? Again, you want to be cautious. You know, sometimes you need correlated errors. Sometimes they make tons of sense. We'll see examples in class where it makes tons of sense. You know, well, I won't go into that now, but sometimes you, a priori, you know you need a correlated error for a variety of reasons. But you want to be careful about just adding them because you think your model fit is going to improve. Like that's never a good way to build models. And, you know, if you have a large number of correlated errors in your model, it can actually produce an under-identified model, even when the degrees of freedom are positive. So when you have positive degrees of freedom and you don't have any correlated errors and you don't have any double loadings, you're for sure going to be fine. But once you start adding tons of correlated errors, things can go a little wonky. So here's a good general rule to live by. For every indicator, there should be at least one other, and this seems, again, very minimal. I'm not suggesting you build models that look like this, but there should be at least one other indicator with which it does not share an error covariance, right? So if you build every conceivable correlated error, you're going to end up having problems. And then, as I said, models that have double loadings tend to be more prone to under-identification. And when you put correlated errors and double loadings together, that can be especially problematic. Am I talking like 1 correlated error and 1 double loading? No, generally that'll be fine. But if you have a big model and you've got tons of correlated errors and tons of double loadings, you can find yourself, again, in a place where the model just won't converge, it won't run. It can be really problematic. So you want to be really thoughtful. And I did put a nice handout that's from Dave Kenny, actually, about what you should be thinking about when you sort of build measurement models. So it's up online, and you should definitely, read through that handout. But this is kind of like the high points from that. All right. Now, this is kind of an odd thing. We've talked a little bit about nested models, right? And I said sometimes it's less obvious to be able to tell whether two models are nested or not. And this is one that's maybe slightly less obvious to you that these two models are nested when at first blush, but I'll explain how they are. So I have a model where I have just one general factor, okay? And then the second model, I have two factors and they're correlated with each other, right? And remember I said in the nested model, you know, I'm going like I've got the same observed variables, I've got the same sample size, and then I can go from one model to the other model either by sort of making constraints, making one or more constraints, or by freeing one or more parameters, right? But I don't do both simultaneously. And when you first look at this, you might think, well, I don't know, is that nested? That seems kind of weird. But if you think about like factor one and factor two, let's just imagine for this, because I think it's easier to think about it conceptually. Imagine we're using a fixed factor variance strategy here, okay? So we're going to fix the factor variances to 1. All right. And in the first model, right, I've got these 4 path coefficients, and I've got my 4 error variances. Fine. And in the second model, I have actually, again, if I fix the factor variances to 1, then I still have 4 coefficients. I have 4 error variances. I now have this correlation, this covariance between the two factors. So it's like I added this one parameter. And if you think about it, another way to think about that is I could start with that 2-factor model, and I could actually constrain that correlation between the two factors to be 1, right? So instead of estimating that correlation there, I could just constrain it to be 1. And if I constrain it to be 1, I'm actually going to get the same model that I get over on the other side, where I have one general factor. So even though at first blush, it might seem like those aren't nested models, it just seems weird, I think, to people at first, they actually are nested models. Does that make sense? So model B actually has, and it shouldn't say one more path. It has one more parameter. So that's a typo. It doesn't actually have an extra path. It's an extra parameter. That parameter is a covariance. So can you send me an email about that so I remember to fix that on the slides for next time? So model B has one more parameter than model A. Make sense? Okay. All right. So now I'm just going to take you really quickly through just a sort of a toy example, not an M+, just sort of theoretical. I mean, just, I've run these models, but we're not going to run them together. We'll run other stuff later. So let's say I've got these 4 variables, okay, and they're all actually these are data from like 100 some years ago, and I think the variables are like it's secondary school variables, and the variables are like classics and physics and English and maths. I think it's called maths because I think they were collected in like Great Britain or something. Anyway, and I have this covariance matrix for it. So I run this model, okay, and the first thing I did actually, just to kind of illustrate another point, which is how sample size is going to sort of affect model fit and other stuff, is I run this model and I say I've got 120 people which is actually, I believe, what the sample size is. So there are 120 people in the sample. I run the model, okay, my chi-square is 4.64 with 2 degrees of freedom. All right, so is 4.64 with 2 degrees of freedom, is that statistically significantly different from 0? No, remember our critical chi-square with 2 degrees of freedom is 5.99. So it's not statistically significant. What does that mean about model fit? Again, we just started to scratch the surface of model fit, but if my chi-square isn't statistically significant, what does that mean?
It means the second model isn't worse than the first.
Well, right now I only have one model. I'm not actually comparing 2 models yet. This is just, I've run this one factor model and the chi-square is 4.64 and it's not statistically significant. So the null hypothesis that I'm testing here is the null hypothesis that the model implied variance covariance matrix equals the variance covariance matrix. So the variance covariance matrix and the model implied variance covariance matrix equal each other. That's the null hypothesis. And of course, remember I said I want to be able to reproduce the variance covariance matrix with my model implied variance covariance matrix. So unlike lots of other statistical tests that you've done in your life, I am rooting for not rejecting the null hypothesis. Here, I really don't want to reject, because if I don't reject, it means, oh yeah, okay, the model implied variance covariance matrix and the actual variance covariance matrix, I'm not rejecting the null hypothesis that their difference is 0, which means they're basically the same, which is good, right? They're close enough, they're the same. So that's what I want. Now notice though what happens when I say I use the same variance covariance matrix, and now I just put in, imagine my sample size is 240 instead of 120. And what happens there? Well, now my chi-square, which is a function of the fit, but also the sample size, it jumps to 9.31, right? So that's quite a big jump. It almost looks like it's double, but that's, I mean, it's not necessarily going to be exactly double. That's kind of that's a coincidence. But now with 240 people and the same variance covariance matrix, I would actually reject the null hypothesis and say, oh, you know, my model doesn't, right? I reject the null hypothesis that the variance covariance matrix and the model implied variance covariance matrix are the same. And that means my fit, right? My model doesn't, you know, fit my data. So the chi-square here, the model's rejected as poor fitting with this larger sample. So this is an important point because we're going to be talking about model fit later today. And the first thing is to remember is that, you know, chi-square is very sensitive to sample size. And if your sample size is big enough, your chi-square, just like anything else, you know, if your sample size is big enough, your chi-square is going to be statistically significant just about no matter what. Okay. All right. So that's kind of my first point. Now, let's look at this. Let's fit the two-factor structure. And now after that, we'll do a test of nested models. So again, for an n of 120, the chi-square is 0.75. And for an n of 240, the chi-square is 1.51. And in both of these cases, because it's a two-factor model, I now only have 1 degree of freedom because I ate up a degree of freedom estimating that correlation, right? But in either case, my chi-square would be retained. So this two-factor model, I mean, again, seems to fit, and we can sort of see that seems to fit even before we do the chi-square difference test, which we're about to do. We can kind of see the two-factor models fitting better than the one-factor model. Yeah? So now let's compare these two models using the chi-square difference test. We can directly compare these models. So let's start with the n of 120. So model A had a chi-square of 4.64. Model B had a chi-square of 0.75. I'm just going to subtract one from the other. I get 3.89. So the difference in chi-square between models A and B is 3.89. How many degrees of freedom difference are there between models A and B? 1. So I'm going to compare that difference, 3.89, to a chi-square with 1 degree of freedom. And the critical value of chi-square with 1 degree of freedom is 3.84. So I just barely cross over that threshold there. But this would actually suggest that even though when I ran model A, it was a good fitting model, right? It wasn't rejected. Actually, when I compare model A and model B is a better fitting model than model A. Does everybody see that? And now I can do the same thing with the sample size of 240, right? So, and we're going to see the same trend, but it's just going to be sort of larger, right? So model A had a chi-square of 9.31. Model B had a chi-square of 1.51. Now the difference between the two models is 7.8. Still a 1 degree of freedom test. And so again, it looks like model B fits better than model A. So that's how the chi-square difference test would work here, right? So in either case, we're gonna favor model B over model A. And obviously, you're not actually gonna do this in real life, just like mess with your sample size, right? This is just for pedagogical reasons. And again, I think it's important because when we start talking about model fit, I want you to understand chi-square is incredibly sensitive to sample size, as I think you can start to see there. So when we compare nested models, right, we've got two models, this base model. Oh, yes, sorry.
Did you talk about the baseline model that gets estimated?
Yeah, I mean, I can. I would like to wait until we get to model fit because we're going to talk explicitly about that then when we talk about the different fit indices. But in a nutshell, the baseline model is basically like the worst possible model, you know? And that'll make more sense why we might care about that as we go along. Yeah, Katie, and yeah?
So I just want to make sure that I understood this. So with the chi-square test, when it's just looking at model fit for the one model, you don't want to reject the null, but then when you're comparing two nested models, you do want to reject?
Well, okay, when you're looking with one model, I totally agree you don't want to reject. I mean, assuming you like your model, right? Assuming it wasn't somebody else's model that you thought was trash and they were like secretly hoping to reject it. But no, generally speaking, with your model, you don't want to reject it. When you're comparing two models, it really depends on, because like, which is the model that you're rooting for? Like, we are always going to favor the simpler model when the chi-square isn't statistically significant, and we're always going to favor the more parameterized model when the chi-square is statistically significant. But I feel like I can't say which one you are hoping will be true because it really depends on, right? Like going back here, if you were trying to say, I think it should be a two-factor model, then you would be happy here. But if you were trying to make the case that like all of these academic areas are all actually just indicators of one general factor, then this would be bad for you, right? So it really sort of depends on what your plan is or what your theory is. Yeah.
In just for a hypothetical sense, if the difference was 3.2, then the conclusion would be that there is not. Could you just like follow up with that conclusion?
Yeah. So like, let's say the difference here were 3.8, right? Because if the difference were 3.8, then we would be saying that the chi-square, the way to think about it is the chi-square for the simpler model isn't that much higher than the chi-square for the more parameterized model. So the chi-squares are sort of essentially, not that different from each other. And when the chi-squares are essentially, close enough, then we're always going to favor the more parsimonious model. It's like Occam's razor, right? So when the chi-square difference test isn't statistically significant, we're always going to favor the simpler model. And when it is statistically significant, well, again, with some caveats here. So like Tamika's on the line here. Tamika she's got data files with hundreds of thousands of people. And so you can imagine that even the for the reasons that I was just talking about with the chi-square being so sensitive to sample size, even the chi-square difference test is sensitive to sample size, right? So, I mean, I'm saying we always favor the more parameterized model, but I mean, technically, I think there are limits to the chi-square difference test. If you've got like an enormous sample and the chi-square only goes up by 4, like I don't know that I would favor the more parameterized model in that case, right? I got 1 million people and the chi-square jumps by 4. I'm not gonna. But like in this situation of like regular sample sizes, nothing extreme, like in this, hundreds of cases rather than like hundreds of thousands of cases, we're gonna favor. And by the way, when I test you on this in exam, I'm thinking of the hundreds of cases situation, not the hundreds of thousands of cases situation. Yes, when the chi-square is statistically significant, we're gonna favor the more parameterized model. But again, I'm going to talk about measures of model fit and how you can sort of think about model fit stuff too, besides just chi-square, because, this is just one sort of crude metric that has its share of problems. The biggest of which is that it's so sensitive to differences in sample size. And that's why all these measures of model fit have kind of cropped up around it. But the logic is statistically significant chi-square difference favor the model that's more parameterized. That means it's the model with fewer degrees of freedom, right? And if it's non-statistically significant, we favor the more parsimonious model. That's going to be the model with more degrees of freedom. And that sometimes throws people off too, because remember, more degrees of freedom means more constraints. We've constrained more things. We have more degrees of freedom. All right. How are we doing on time? Okay, so, okay, we already talked about that. I mean, and obviously, when you use the chi-square difference test, not only should you, there's going to be one model that's better than the other, or maybe they're the same, but ideally, not only are you comparing two models, but the one that you pick should also be a good model, right? So if you could theoretically do you could compare two models, both of which fit horribly. And yeah, one might fit better than the other, but that's not exactly a rousing endorsement, right? Do you know what I'm saying? So that's kind of my last my last point is if the more complex model should be a good fitting model. Otherwise, your conclusion is just going to be well, this model isn't as bad as this one, but they're both kind of dogs, right? So, which is of course not what we're hoping for. Okay, so back to sort of thinking about CFA. In our measurement models, we would like items that are measured or indicators. We would like those to have relatively high loadings on the factor, right? I mean, ideally, this is just sort of conceptually. And we'd like and this is the more important, well, they're both important points, but the correlations between factors shouldn't be sort of excessively high. And this is sometimes in the measurement literature referred to as discriminant validity. And I've put a greater than 0.85 here, but again, I don't think of this as an absolute benchmark. If your correlation between your factors is 0.84, everything's great. And if it's 0.86, everything's horrible, right? It's more of the way I think of it is if the correlations between two factors are greater than about 0.8, I start to get worried. Now remember, these are correlations between latent variables, not observed variables, so those correlations are going to be higher than the correlations between two subscales. But even so, once I'm above 0.8, I start to get worried about discriminant validity. Once I get above 0.9, I am super not happy. I'm really, really feeling like I have discriminant validity issues. And so in that 0.8 to 0.9 range, is it's called the yellow light, It sort of depends a little bit on your theory and lots of other stuff. But once you've got correlations between factors that are above, 0.85 or 0.9, you're definitely getting into the land where you start to ask yourself, am I really measuring two different factors, or am I just measuring basically the same factor with sort of two different sets of items? Again, in the extreme, if the correlation between two factors is 1, then clearly that's one factor, right? So where do you draw the line down from 1? Some of this is going to be your own personal comfort level. This is probably 15 years ago now. I was working on a CFA for a group of people, and they had these pedagogical content knowledge items, math pedagogical content knowledge. And some of the items were multiple choice items, and some of the items were open-ended items. And they were really convinced that the multiple choice items were really a different factor than the open-ended items, because, it's just different process that you use to answer multiple choice items. And, you have to do more steps for the open-ended items. So, they said, okay, there are these two factors, right? This closed-ended math pedagogical content, and then this open-ended math pedagogical content knowledge factor. So I ran the confirmatory factor analysis. And when I ran the CFA, the correlation between the two factors was 0.99, right? So this is kind of obvious. Like we could quibble about 0.84, 0.86, but like if you get to 0.99, that's like, so I went back to them and I was like, this is not two factors. They didn't want to hear me, of course. No, we really believe it's two factors. I'm like, the correlation is 0.99. You're measuring, like I get that you think it's really important that some of the items are open-ended and some of the items are multiple choice, but like what I'm seeing from this factor analysis tells me they're all tapping into this one general factor about mathematical pedagogical content knowledge. So that's kind of an example of like discriminant validity issues. So when we're looking at confirmatory factor analysis results, what are we going to be looking at in the M+ output? Because we didn't do this last time, right? We're going to look at all of our parameter estimates, and we want all of our parameter estimates to be statistically significantly different from 0. We want our factor loadings to be different from 0. Obviously, if a factor loading isn't statistically significant, it's telling you that that factor doesn't predict that indicator, right? That's not a great indicator then. And that's like, again, a rock bottom minimum. I'm not saying that should be your threshold for what's an important, is high enough, but I'm just saying, of course they should be statistically significant. I'd like my factor variances to be statistically significantly different from 0. Why? What would it mean if my factor variance isn't statistically significantly different from 0?
If you ask you a question.
Sure. I want the factor variance to be statistically significantly different from 0. Imagine I have a model and I'm estimating a factor, and the variance of that factor is not statistically significantly different from 0. And again, this presumes I'm using a marker variable strategy, right? What does that mean if the factor variance is not statistically significantly different from 0?
Just the same as your marker.
Well, it's in the metric of the marker variable, but if the variance isn't statistically significantly different from 0, it means there's no statistically significant variability in the factor. So people don't differ from each other on this factor, right? Which is, I like to call this a latent constant. We're going for a latent variable, not a latent constant, right? Like if the factor variance is 0, it's not a variable. Anything with a variance of 0 isn't a variable. And that's true for a latent variable too, right? So if we don't have enough variance in the latent variable, that's just, like I said, it's like a latent constant. So that's problematic. Why do I say you would use a one-tailed test for factor variances and error variances? Yeah, exactly. Although you will see that they can in SEM, but we don't want them to be. So we think of variances as always being, positive, right? Or I suppose 0 is your lower bound. So when you test variances, you generally use, a one-tailed test, or sometimes people use chi-square, because remember, we talked about how chi-square is actually bounded by 0 in a prior class. So we use a one-tailed test for error variances, two-tailed test for correlations, because of course correlations could be positive or negative. I guess I should say, I said everything should be statistically significantly different from 0, but I don't necessarily care if my error correlations are statistically significantly different from 0. I would drop it out if I didn't need it. So why would I want my error variances to be statistically significantly different from 0? I said why I would want my factor variance to be statistically significant, but this is error. So why do I want to have statistically significant error in each of my indicators? Wow. Flip that question on its head and say, what would it mean if you didn't have error in one of your indicators?
That is measured perfectly.
Yeah, exactly. It would mean that the factor perfectly measures the indicator. And what would that mean about the correlation between the indicator and the factor? It would be 1. And then what would that mean about your factor? Yeah, like, yeah, right? It's just like, is it total? That's a problem. No indicator should be redundant with our factor, right? The whole idea is our factor is latent, and there are multiple indicators, and our factor is sort of measured by multiple indicators. If it ends up that one indicator is, like there's just no error variance in this one indicator, that really means this factor and this indicator are basically redundant with each other, which means like maybe all you need is that indicator and not a whole factor, right? So we do actually, Mike, it seems counterintuitive at first, like it's error. I don't want error. I mean, it's good if we can explain most of the variance in our indicators, but we don't actually want to be explaining all of the variance in any of our indicators. Yeah.
Does that essentially mean that the observed score is the true score?
It essentially means the observed score is what?
The true score.
Yeah, I mean, it means that the observed score on that item is basically redundant with the factor variance. I mean, I don't know if I want to go so high as far as to say it's the true. I mean, it is redundant with the true score. But I mean, I guess I would question whether I would start to question that whole structure, right? So that's why I'm kind of hedging on saying it's the true score. But it does mean that the true score, as defined by the factor, is redundant with the indicator. But then I think that sort of calls into question the whole factor structure, right? Like that gives me real pause. Like that's not good. So we don't want that either. And then there's another reason that's the first reason. But there's also another, like maybe more technical reason that we don't want to see non-statistically significant error variances. And that's because, so we're using maximum likelihood estimation, right? To come up with these estimates of all of our parameters. And it could be that the estimate that sort of maximizes the likelihood, the parameter estimates that maximize the likelihood of sort of observing our data, you could actually end up with an error variance that is negative. But that's a problem, right? Because we know that variances can't be negative. So anytime you end up with a negative error variance, that's what we call a Haywood case. I don't know why it's called a Haywood case. I don't know who Haywood was, if he was the first guy that noticed this. I should look that up. But they're called Haywood cases. So a Haywood case means there's a negative error variance. And if you see and the other kind of inadmissible, and that's what's called an inadmissible solution. So when you look at your results in M+, not only do you want to see that, you get results, right? And you might say the model estimation terminated normally, but you also want to make sure that your results make sense. And so if you get one or more error variances that are negative, you have to say to yourself, well, that doesn't make sense. That can't be right? So I now don't really trust my results because I've got a negative error variance. Another thing that can happen is again, these things luckily don't happen very often, but they can happen. You could actually end up with a situation where you get a correlation between two factors or two somethings, often it's factors. You could get a correlation between two factors that's higher than one. Not a covariance. Covariance could be anything, but a correlation. So if the correlation between two factors is higher than one, that's also not possible, right? Because correlations have to be between -1 and 1. So when you're running these models, these are things that you absolutely want to look at in your output. If you see negative error variances, or if you see correlations above 1, those are both signs that something is awry, that something is problematic. And so then you sort of have to dig in. I mean, there's a little bit of detective work that goes on there to try to figure out, like, what's wrong? Why is this happening? And again, I'm not going to belabor how to do that detective work right now, but I think it's very important for you to be looking for these things. And this is going to sound weird, okay? But so one of the other reasons that non-statistically significant error variances bother me is an error variance that gets too close to 0 is like a little bit too close for comfort in my mind of crossing over into a potential Haywood case, if that makes sense. So like it conceptually is problematic, and it is also technically somewhat problematic. Like, I've definitely had scenarios where, you know, you're fitting a series of models, and like in one model, you know, because they're competing models, and in one model the error variance is like 0.001, so it's like, you know, technically positive, but it's really, really small. And then the next model, it goes negative, right? Like, so I get very uncomfortable when my variances start to get too close to zero, because I also think, oh God, you know, maybe I'm on the way into a Haywood case. So that's another sort of reason to not like that. Okay, pattern factor loadings or pattern coefficients. We can interpret these just like the standardized ones can be interpreted like standardized regression coefficients, right? And these are really just direct paths between the factor and the item. And when we use the standardized solution, then the standardized factor loading squared. So let's assume that there's just, you know, an item is being explained by just one factor. So we've got like a unidimensional solution here. So if I've got the factor predicts the item, and there's only one factor predicting that item, then, well, actually, I can do this even if there's more than one factor predicting the item. But the standardized factor loading is the proportion of variance in the item that's like directly explained by the factor. The factor, if the item loads on only one factor, yeah. So if the factor loading is 0.7, that means the factor explains 49% of the variance in item one. And the reason that I'm kind of hedging is like if the item loads on only one factor, because remember, if an item is loading on two factors, then the standardized factor loadings are like direct effects. So now it's like the how much does this factor predict this item after controlling for the other factor? So for just the same reasons that we have to sort of be careful in multiple regression about how we talk about, you know, what those regression coefficients mean in multiple regression, right? It would be like independent with more than one factor is like the independent contribution of the factor to this item. So that's what I'm saying. If X1 loads on multiple factors, then the standardized loading is interpreted like the standardized regression coefficient that takes into account the correlations among the factors, right? Takes into account the other factors, and it takes into account the correlations among the factors. Usually we have a unidimensional solution though, so it's really easy to just say factor loading is 0.7. That means the factor explains 49% of the variance in this item. And then that means, of course, that 51% of the variance in the item is not explained by the factor, right? So a factor loading of 0.7 always tells you about half of the variance is explained by the item and by the factor. Half of the variance in the item is explained by the factor and about half is not. I don't think I'm going to do too much with this. I think I'll skip these couple of slides just for the sake of time. But in the next couple of slides, I show you how you can actually convert from unstandardized to standardized path coefficients. And it's really actually quite easy. It's just like converting from unstandardized to standardized regression coefficients in multiple regression, right? So if I have an unstandardized estimate, I just multiply the loading by the standard deviation of the factor divided by the standard deviation of the measure. And that's exactly analogous to what you would do in multiple regression. So, okay, so I said I was going to skip it, but I'll just say briefly. So for example, here I've got a marker variable. The variance in the indicator is 3.059. The variance in the factor is 2.798. Okay, so here is my unstandardized regression coefficient is 1. And then I'm going to multiply that by the square root, because these are variances, the square root of the variance in the factor divided by the variance in the indicator. And then that gives you 0.956. So I could do this all the way down the line. So it's really, my point is, it's really easy to go from unstandardized to standardized loadings. You never have to do this, by the way. I mean, you're always going to get the standardized and unstandardized loadings in the output, but in case you're interested, that's how it works. Yeah.
Is this like why when, like, so C here is a marker variable, And that's why the marker variable unstandardized has a coefficient of 1, but standardized has a coefficient of like 0.9.
Mm-hmm.
Okay.
Yeah, exactly. And so, and remember, like, you know, we're usually not going to be all that interested in this unstandardized solution, right? And the unstandardized solution can look really different depending on what you use as the marker variable. Because remember, you know, whatever marker variable you use is going to be constrained to have a coefficient of 1. So generally speaking, like you could see here, and again, this is in general, generally speaking, you can see like this marker variable of 1, notice how all the other unstandardized coefficients are less than 1, and now look, all the standardized coefficients are actually less than my marker variable. That kind of makes sense because that unstandardized solution is all sort of a little bit of function of the marker variable. So sometimes, like if the marker variable is your weakest indicator, you'll see that the coefficients for the other variables will actually be greater than 1 in the unstandardized solution. You know what I mean? Because your marker variable is not your best indicator. But it's way easier to interpret the standardized coefficients. And again, when you run like, you know, exploratory factor analyses, usually you only get standardized factor loadings. So it's pretty, generally speaking, for single groups, we really only are interested in the standardized loadings. Yeah. Okay. So I talked about how we can convert that. So the percentage of variance that's explained by the factors, well, here, if they're, you know, we can take the ratio of the unstandardized measurement error variance in an indicator, and we can divide that by the observed variance in the indicator. So, for example, I think we had an example there where like 3, the observed variance in the, was it the indicator or the factor was 3? Hold on, let me go back up here. Yeah, the variance in the indicator was like 3 here, let's say, or let's use the one that's 4. So the variance in the indicator is 4, right? And so if I look at what's the proportion of, like, what's the variance, let me go back over here. Here we go. So what's the, you know, how much error variance is there? So let's say I have the observed variance is 4 and the error variance is 2. So now I'm looking at the unstandardized error variance, okay? Then what would that mean? That would mean out of that total variance of 4, 2, right? 2 of the variance, 2 is not explained by the factors. So I take 2 divided by 4, and that means 50% of the variance in that indicator is not explained by the factors. Or let's say it's 1. I feel like I used 50% a bunch. So let's say the error variance is 1 and the actual variance in the indicator is 4, right? But the error variance is 1. Okay, well that means that 25% of the variance in this indicator is not explained by the factor or factors. It could be multiple factors. And then I would say 1 over 4, right? That means 25% of the variance in the indicator is not explained by the factor. So how much is explained by the factor? 25% is not explained, 75% is explained. Yeah. So sometimes it seems weird to people at first that you've got the error variance. So you're always going to end up with like, what proportion of the variance isn't explained by the factor, right? And then you're going to have to say, oh, okay, well, 1 minus that proportion that I don't explain, that is what I am explaining. Does that make sense? Okay. So like I said, in problems with CFAs, discriminant validity can be an issue. Haywood cases can be an issue. Empirical under-identification can be an issue. So like theoretically, my model should be identified. But when I try to run it, it just, you know, with this variance covariance matrix, it doesn't run. And lack of convergence. Lack of convergence means I try to run this model and I never actually get, a solution. So my model never converges on a solution. We're going to talk a little bit more about estimation, not this week, sometime soon, but I'm trying to come up with this maximum likelihood these maximum likelihood estimates, right? So I'm trying to sort of find a maximum. And it can be the case that like, you know, I'm using this iterative technique, and it could just be the case that like I never actually hit the max. So I just kind of like, you know, running, and the model never converges. What are the things you can do when that happens? Doesn't work as often as you might like. It's just up the number of iterations. So like, I forget what the default number of iterations is in M+ for a model, but you know, you can always crank up the number of iterations. So if like something doesn't converge in 50 iterations, give it 100 iterations, give it 200, give it 1,000. But my experience is like, you know, usually if it doesn't converge in whatever the default number of iterations is for M+, you know, doubling the number of iterations often does not help. Sometimes it does, but sometimes it doesn't. So that's often sort of shows you there's a problem with your model. So obviously, any of these things can be problematic. If you can't get a convergent solution, that's bad, right? If it's empirically under-identified, you're also not going to get a solution you can use. Haywood cases, or you can't report correlations above 1 in your paper, or negative error variances, you're going to get eaten alive, right? So all of these things are problematic. And we already talked about discriminant validity, so I'm not going to say any more about that. So we talked a little bit about Haywood cases. What can I do? I mean, I'm going to try to respecify my model. There are lots, like maybe I just did something dumb. Often I did. Like often when this happens, there's maybe an obvious respecification you should try. There are some other things you can do. You can create a nonlinear constraint on loading. We're not going to talk about that in any more detail right now. You can fix the standardized loading to 1, you know, which is like kind of a cheaty way to solve the problem, right? You can set loadings equal to each other. Again, that's got to make sense. You can fix the error variance, like if it's going negative. Again, this is a cheaty thing to do as well, but like, so let's say that error variance is, you know, negative 0.03 or something, right? You could fix the error, you could rerun the model and fix the error variance to be a small positive number. Now, those things will work, but you know, that's sort of, I feel like that's a little bit of like, I don't know, lipstick on a pig or something, right? You know, you don't want to, that is not where I would go first. It's like, oh, I'll just fix the standardized loading to 1, or I'll fix the error variance to a small positive number. You definitely should try to get to the root of the problem and see what's going on. But you know, occasionally that might make sense. And again, you know, when the model's theoretically identified, but with your variance covariance matrix, the model's not identified. So I gave that example of, you know, a 2-factor model with 2 items, and the correlation between the factors is 0. That's the thing where, like, before you run the model, you wouldn't know the factor correlation is going to be 0, and so the model is identified when you're thinking about it, but just the data you have, you know, it's not actually identified with your variance covariance matrix. How will you know that's going on? Well, often those models won't converge, so just run forever. Or the other thing that you'll see when you've got a problem with empirical under-identification is you'll get like enormous standard errors and really wild parameter estimates. So you'll, you know, like run your model and, you know, you look at your output and you'll see like, you know, like a standard error of like, you know, 30, whatever, something huge, like 30 or 30,000 or whatever. Or you'll see parameter estimates like, you know, they just don't even make sense. Sometimes they're unstandardized parameter estimates that don't make sense. Sometimes, well, often standardized ones don't make any sense either. So you'll see, like, but it's really important before you start interpreting your models that you make sure that the output that you get is sensible. The good news is that this doesn't happen most of the time, you know, but it can happen. So the onus is on you to, before you start interpreting stuff, to make sure that it actually makes sense, right? You know, you don't want to be like submitting stuff that doesn't make any sense. So yeah, okay. So, if you will get empirical under-identification problems if your indicators aren't correlated with each other. I already said this, if the marker variable doesn't correlate with other indicators. I mentioned the 2-indicator situation. And then this is kind of interesting, but like with 3 indicators, you can end up with empirical under-identification if the product of the 3 correlations is negative, which is just kind of like an interesting thing. So you got 3 indicators and the product of the 3 correlations is negative. That can actually cause identification issues, which is not maybe obvious at first that would happen. Oh yeah, so for lack of convergence, I said you could up the number of iterations, but it usually doesn't work. You got to make sure you haven't done something dumb. Often when things don't converge, you'll find a stupid typo. You know, you forgot a semicolon, and so it's reading 2 lines as one, right? I mean, a lot of times it's just like, you're like, oh, duh, okay. Another thing that you can do is you can actually use starting values. So we're using this iterative technique. So the computer, right, M+ is sort of starting with it's gonna like just come up with some parameter estimates just to kind of get the ball rolling, and then it's going to kind of iterate back and forth. So you sometimes, this luckily doesn't happen that much anymore. This used to be really problematic in the old days. You know, sometimes if you don't have good starting values, like you can end up with non-convergence, and if you just give better starting values, you can actually get a convergent solution. One of the things that's interesting, so usually this doesn't happen, but if you don't get a convergent solution, most of the time M+ will actually print out where it stopped in terms of parameter estimates. So it'll like give you for all of the parameters, like what its final estimates of those parameters were, even though it didn't converge. And so one thing that can sometimes work is you basically just take those estimates and you plug them in as starting values and let it crank again. And sometimes that'll help. But, and then sometimes there's just no solution. Like, I mean, I feel like whenever we get into advanced modeling techniques, we all start to get like a little bit greedy, you know, like, and we start there. Sometimes the model is just too complex for the amount of data that you have, right? Like, yeah, that's a cool model. And you could estimate that model if you had like 5,000 people, but you're not gonna be able to estimate that model with 50 people. I talked about the fact that degrees of freedom are actually a function of the difference between the number of unique variance covariance, unique variances and covariances, and the number of parameters that you're estimating, and that is absolutely true. But you need to have more people than parameters you're estimating, even though that has nothing to do with the degrees of freedom that you are looking at. So like, if you're trying to estimate a model that has 100 parameters that you're trying to estimate, and you have like 90 people, it's not going to work. I mean, it shouldn't work. If you get it to work, come and see me. That's interesting, but it shouldn't work. And like, even if you have 100 free parameters and you have 102 people, like, odds are good it's not going to work, right? So like, sometimes your model is just too complex for the amount of data that you really have to support that model. And the solution there is obviously get more data. And so people will often ask, like, what's the minimal, we could talk about power analysis, and that's like one way of thinking about sample size. But another way of thinking about sample size is like, what's the minimum sample size to get this model to run and like have it converge and give me reasonable estimates, which is not the same thing as power, right? And I can't tell you, I mean, you'll hear these rules of thumb, like you should have at least 200 people to run a model. I mean, I kind of live by that myself, but all of those are just like, they're just that. They're rules of thumb. It really depends so much on how complicated the model is. If you have a very simple model with few free parameters and few variables, like you might be able to get the model run with 100 people, and if you have a super, super, super complicated model and a lot is going on, you might need, closer to 1,000 people. So it really does depend on the model, not just, there is no like, yes, 200 is it, you can do any model you want with 200. I think people tend to say 200 because, that's just, for sort of garden variety models, 200 usually kind of gets you on the board, but it's not like a strict rule of thumb. I thought I saw a hand. Yeah, Hannah.
Yeah, so maybe I missed this, but when you say starting values, do you mean like the things that we decide before the model, like fixed? Like,
No. Oh yeah, sorry. So starting values are, so when we get the parameters, right, we actually have estimates for every parameter. So we have an estimate for the error variance. We have an estimate for the factor covariance. We have an estimate for the factor loading, right?
Yeah, like the data that we feed into it.
Well, the data that we feed into, feed into it gives us those parameter estimates. Starting values are like the computer is going to give, it's just going to give us, it's going to say like, just to get started, like it's going to give a value for each free, it's going to start somewhere.
Okay.
Even though you're freely estimating the parameter, the computer program is going to start somewhere. And so often it'll just like give starting values for some packages. It'll just give starting values of 1, for example, for like every parameter that you're freely estimating. And it shouldn't matter. It shouldn't matter what the starting values are because it's using this iterative procedure. So it'll just get where it's going. But sometimes starting values can be, sometimes it could be the case that the starting values that it's starting with are really bad. I forget exactly how M+ generates its start values. I'll check on that and I'll tell you next week. For multi-level modeling packages, the starting values are usually just the OLS estimates. So like runs an OLS regression and it feeds those in as start values for the multi-level model.
They're constructed from the sample statistics.
There you go. They're constructed from the sample statistics. So M+ has got an algorithm that it uses to generate starting values, but sometimes that might not work as well. So sometimes it's helpful to kind of prime the pump. I have not found this to be a real issue. I mean, usually with M+, it does a good job and it's not a problem, but certain, again, so sometimes in the olden days, with other packages, this used to be a much bigger problem. And in fact, Don Hedeker was talking about fitting these nonlinear mixed effects location scale models, which are slightly different models with SAS NL mixed. And he made this joke that has always stuck with me that it works great as long as you know what the answer is up front. Because if you put the right starting values into the package, it would give you results, right? But if you kind of didn't know where you were going, so you couldn't give good starting values, the package would just not converge. Again, that's not generally too much of a problem with M+, but it's something that it's good to be aware of. This would be a good time for a break. What time is it? 11:05. Okay, so let's take right till 11:15. Oh man, we only have an hour left, huh? Okay, so we've got to make sure to do some M+ stuff. We didn't even talk about hybrid models. Oh my God. Okay. Okay, I'm not going to do those. Oh, let me turn off the recording for a sec. Okay, I'll resume recording now. Okay, going into M+. Okay, share application. I think, right? Okay, window, M+, share. Okay, there we go. So that should be shared now. Okay, so I'm going to go to File, Open, and I'm going to find my M+ input here somewhere, desktop, week 4 M+. And you can see I've got 3 models here. So the first one's going to be the measurement model, then the just identified model, and then the conceptual model. So let's go ahead and open. And okay, so title, data. This is actually individual data, so I don't need to say anything about correlations or anything. The variables are, and here they are, we've got now these indicator variables. Use variables are, and I've got all of those the same variables. I'm using all the variables in the file here. And then missing are all equals -99. That's my missing value code. So I've got that in there. So that's all basic. So now let's look at our model. So here's what I've got. Self-perceptions is measured by these 3 indicator variables. Goal valuation is, and let's see, it's 20, 13, and 11. Goal valuation is measured by these next 3 indicator variables. Motivation self-regulation is measured by 3 indicator variables, right? That's what you saw on that picture. And now, I didn't really talk about this, but in this measurement model, there's one correlated error between S20 and S29. So if we had done our example last week, we would have seen this correlated error, but we didn't do that example. But we'll just leave it in there. So that, remember, this is a correlation between the errors of 20 and 29, not actually between the variables. And now I want to make sure that I actually build in correlations among all of the exogenous variables. Now, technically, again, M+ should by default correlate all of the exogenous variables. So I shouldn't actually need to say all of this, but I'm going to say it anyway, just because I think it's helpful to be really explicit here when we're doing this. So I'm saying that GPA is actually correlated with self-perceptions, goal evaluation, and motivation. Homework is correlated with self-perceptions, goal evaluation, and motivation self-regulation. Homework is correlated with GPA. And actually, well, I should have said self-perceptions. I didn't say all of them, did I? I didn't say that self-perceptions, here, let's see, self-perceptions is correlated with, I'm having trouble seeing the screen. Oh, that's because I didn't make it big. I should make it big, right? That's my problem. Hold on. Edit. Change font. I'm having trouble seeing it. You must also be having trouble seeing it, right? 22. Okay. There we go. So self-perceptions with, oops. Uh-oh. Why does it look so weird? Well, we'll see what happens. With goal valuation. Not G. Valuation. Okay. Whoops. And let's see. Did I get them all? Did I miss any? I mean, technically, again, they're all exogenous, so I'm going to get them all anyway, but I'm just trying to be thorough here. With Mozart, did I not do that one? You're right. Okay, so I probably need that one I need Moat SR with self-perceptions, and then I probably need it with goal valuation too, right? SR with, oh, thank you. That will make a big difference. Both reg with self-P and with, what did I call? Goal V, right? Yeah? Well, no. It's going to go like, you have a you. Okay, and I'm going to save that and run it. Heck, it ran. That's good. Okay, so here's my measurement model. Oh, by the way, if I go to, let's go to the diagram first. So view the diagram. Okay, it's kind of ugly, but again, it's good to check, right? Okay, so you can see that we've got all of these are all of my, all of these variables are now like exogenous variables. And you can see, it might seem, and this is kind of where I would draw the distinction between like measurement model and CFA. I mean, a lot of times when people say CFA, they wouldn't necessarily put GPA and homework in here because they're just observed variables. But in this measurement model, we're going to put in all of our conceptual variables of interest, whether they're latent or observed. And you can see here, like, what if I wanted to see standardized estimates? There we go. And maybe I don't want to see the standard errors because it looks a little busy, right? Did I get rid of the standard errors? Hold on. No, I got to say no standard errors, not no estimates. Show only estimates. There we go. So there you go. So these are my standardized parameter estimates that are standardized parameter estimates. So that's my measurement model. Does that make sense? Did everybody get that? Did everybody get some output?
There's an option, a standardized y-x estimate. What does it show? Because I thought that shows a standardized estimate.
Oh yeah, there you go. Standard. It's actually not going to matter with the because we have continuous variables here. It's not going to matter. STDYX and STD are going to give you the same thing. It's really only when you have categorical variables that they're going to end up being different. But anyway, yeah, we should use STDYX. I agree.
On our homework, is that the sort of pathway that you always want us to do too? Like U, residual arrows, STDYX, estimates, show only estimates, show covariance. Like, are those 4 the ones that we just kind of always want to check off?
Yeah, I mean, you could show. It's really up to you whether you want to show standard errors or not. I think it's useful to look at the standardized estimates, especially for the measurement model. Actually, even for the regular model, I think standardized is more useful. Usually, easier to interpret. Yeah, and then standard errors is really up to you. I think, but the standard errors get busy, so I think it's easier to look at it without the standard errors. You know. I don't know. Is there anything else we gave specifically as for the homework?
Yeah, I'm looking at that right
Okay.
now.
So now let's take a look at our output. Where did our output go? Here it is.
Standardized estimates.
Okay. And I think whether you have standard errors or not, I don't think we really care.
No.
But it certainly is easier to look at without them. Okay, so first we get all these sample statistics, which we're going to kind of breeze by right now. And now we're going to look at let's start by looking at our chi-square tested model fit. So here, our chi-square tested model fit is, and I'm going to write this down too. What is it? It's 49.557 with how many degrees of freedom? 35. So I really should go like chi-square 35 equals 49.557. Okay. And we could, although I'm not going to do that because I don't want to waste too much time, but we could figure out, right? Well, we know all the 35 degrees of freedom come from the measurement part of the model, right? They're not from the structural part of the model. We could do our counting, but I'm not going to do that right now. I'll leave that for you to do. Here are our model results. So first we get the unstandardized estimates. Let's jump down and we really want to kind of look at the standardized estimates. And you can see here, like, I notice some things like, oh, okay, really looks like my standardized factor loadings are pretty good, right? They're all pretty healthy and big. They look fine, right? And now I definitely want to look at the standardized when I look at these with statements, because I should make this bigger too, right? Let's see, change font. And let's go. Okay. Oh, that's really big. Okay. Where did my correlations go? Here we go. Here are my correlations. So this is kind of interesting too. So I can sort of see what are the correlations between, like, my latent variables. And you can see motivation and goal valuation are really pretty strongly correlated with each other, right? I think let me make sure I'm in my standardized. Yeah, I am. Okay. Those are pretty strongly correlated with each other. Whereas, like, let's see, you can see it's interesting. Here we go. Goal valuation, how much you value the goals of school, is actually not statistically significantly correlated with GPA, which is interesting, right? That correlation is 0.036 and it's not statistically significant. But again, I mean, I'm not in the part where I'm doing conceptually omitted paths and all that stuff, but I'm just kind of pointing out that, here are my correlations. I would definitely want to be making sure I don't have any crazy, I'd look at the unstandardized to make sure I don't have any problems with Haywood cases. So my residual variances are all statistically significant. That's good. The variances of my latent variables, again, this I want to look at from the unstandardized solution. They all look good, right? You can see the variance of goal valuation is lower than the variance of, like, self-perceptions or motivation self-regulation, but they all still look good. Okay, so Okay, so my measurement model looks good. And this never is going to happen in real life, but there's not too much to do here because it actually fits well. Where'd my model fit? Right, chi-square 35. What was my p-value? 0.0524. So technically, right, it's above 0.05. My model fits the data. There's not statistically significant misfit between the model and the data. Yay! Okay, so we're moving along. So my measurement model fits well, but if it didn't, this is where I would be making some modifications, right? Like, oh, my measurement model doesn't fit well. What's going on? But luckily, we don't need to do that. So we're going to move to the next part of the model, not the model, but okay, example. So let me save this, by the way. Save. So let's go to our next, go to open the just identified conceptual model. So notice here, yeah?
We have a question about the variances because I didn't catch what you went over, but it looks like they're all like one.
Oh, you're looking at the standardized one. So you want to, for the variances, look at the unstandardized solution.
Both residual and regular.
Yeah, because variances are always going to be one for the standardized solution, right? So when you're looking at variances, you want to look at the unstandardized solution. But when you look at like the loadings and the correlations, you want to look at the standardized solution. Yeah, sorry, I did go through that kind of fast. Okay, so now we've got our model that has the conceptually omitted paths in there, right? Our just identified model. So here I still have my by statements, right? For this, I still have this correlated error, but now I'm saying GPA is regressed on self-perceptions, goal evaluation, motivation, self-regulation, and homework, right? Homework is regressed on self-perceptions, goal evaluation, and motivation, self-regulation. Motivation, self-regulation is regressed on self-perceptions and goal evaluation. And you can see, I didn't here say, but I could, that like academic self-perceptions and goal evaluation are correlated with each other because those are still exogenous variables. So it's going to be, those are going to be correlated by default. So, but if I wanted to, I could, to be complete, I could say self P with goal V. There we go. And those are correlated with each other. So save. And then we just run it. And just to remind ourselves, in this model, I'm only going to be looking at 3 parameters. Remember? I'm going to be looking for those 3 conceptually omitted paths, which maybe you don't remember what they were from last time. So I'll just remind you, it's academic self-perceptions and goal evaluation to homework, right? I got to remind myself. Is that right? And motivation to GPA. So we run this. And we're going to go, I should have marked them on here, my conceptually omitted paths. So let's start by going to the conceptually omitted paths. And I'll go to the standardized results. That's fine. Okay, so here we go. So I don't really have to worry about these by statements at all anymore because I've already looked at the measurement model. So I'm not worried about that. I'm looking at my first conceptually omitted path, remember, was motivation on GPA. And we can see that actually that path is not statistically significant. Did everybody see that? The p-value is 0.207. The path is 0.107. So motivation to GPA, which was one of my conceptually omitted paths, doesn't look like I need that. The other 2, am I right? That it was academic self-perceptions and goal evaluation to homework after controlling for motivation. I'm sure I'm right about that, actually. Yeah. So, and yeah, it's these 2. So the other 2 conceptually omitted paths that we didn't think we needed were homework regressed on self-perceptions and homework regressed on goal evaluation. Mm-hmm. And so we were thinking after controlling for motivation, we don't need a direct effect of self-perceptions on goal evaluation on homework, but we're checking. Like we didn't have those in our conceptual model, but we're checking, make sure we don't need them. And sure enough, as is the case when you get to make up the examples yourself, turns out, right, we don't need those, yay. So I can actually delete those 3 paths that I thought I didn't need. So this was my just identified model. I delete the 3 paths that I don't think I need, right? And then I'm going to run my conceptual model. So to do that, here, I can come over here. I'll just open up the conceptual model. Okay, so you can see in the conceptual model, I got rid of homework is only regressed on motivation self-regulation because we got rid of the paths from goal evaluation and self-perceptions to homework. And you can see that GPA is regressed on self-perceptions, goal evaluation, and homework, but there's no direct path from motivation to GPA, right? So those are the 3 paths we just checked and we just confirmed. Oh, you know what I didn't look at? Shoot. In the last one, hold on. Let me go back there for a second. Just identified, run. Okay. One thing I did want to point out to you, though, the chi-square, exactly. I wanted to point out to you that this chi-square for this just identified model, so going back to model 2, is exactly the same as the chi-square from the measurement model. Do you see that? But I can't get those tests of deleted paths from the measurement model, right? That's not possible. So, but I have the exact same chi-square, 49.557 with 35 degrees of freedom. So I don't actually need to write that down again. So now let's go to our model 3, though, which is our conceptual model, which now we're deleting all 3 of those paths simultaneously, and we're going to run that model. And now this model, how many degrees of freedom are there going to be in this model that I just ran without peeking? This last model had 35 degrees of freedom. How many degrees of freedom in this model? 38, right? I deleted 3 paths that bought me 3 degrees of freedom. So this is going to have 38 degrees of freedom. What's my chi-square going to be? It's going to be at least 49.557, right? It can't go down. Got to go up. How much does it go up? That's the question. So here we go. It's 53.49 with 38 degrees of freedom. Write that down. Okay, so we've got the chi-square for the, so this is the chi-square for the just identified model, and this is the chi-square for the conceptual model with 38 degrees of freedom is, what did I just say?
53.49.
53.49. Yeah, let's make this easier on ourselves and just go to hundreds, right? So now I've got the chi-square for this model is 53.49 with 38 degrees of freedom. So I can say 53.49 with 38 degrees of freedom minus 49.56 with 35 degrees of freedom. And I get, thank you, 3.93 with 3 degrees of freedom. Is that chi-square difference test going to be statistically significant?
No.
Definitely not, right? 3.93 with 3 degrees of freedom, that is less than the 7.8, whatever it is. And so we get, this is a non-statistically significant chi-square. So which model do we favor? The simpler model, right? We can, so, which is not surprising because we saw that we could, right? I mean, in some sense, it's not very surprising because we deleted paths that were not statistically significant. So it's really no surprise that after deleting 3 non-statistically significant paths, that the model fit is essentially the same. You know, it's not like we deleted a path that had a large coefficient or anything. So not too surprising. But again, this chi-square difference test, what we get from this so when we looked at each path separately, we saw each path separately was not statistically significantly different from 0. This chi-square test says, hey, you can eliminate all 3 of them simultaneously. This is like a multivariate test, right? We can eliminate all 3 of them simultaneously and still the model fits equally well. So it's a little bit different from just looking one path at a time, but having said that, generally speaking, if you look one path at a time and you only get rid of things that are not statistically significant, it'll usually turn out that looking at the three as a package will also not actually deteriorate model fit significantly, right? Which, I mean, logically makes sense. And now, I mean, you can see this model. So again, this is where you don't want to be too much of a slave to p-values. The old model had a p-value of what? 0.053, I think. 0.05 something. This model has a p-value of 0.049. So technically, this model doesn't fit, and the last model did fit, and yet this model and the last model fit equally well. Which is why I think the chi-square difference test is a much better way to sort of gauge how to compare this model to the last model versus going, oh, the last model had a p-value of 0.051 and this model has a p-value of 0.049, so the last model must be better. I think that's flawed logic. Yes, Hannah?
So which, okay, I think I got lost. So which one in this case is the simpler model? Because
this is the simpler model. The one with the 38 degrees of freedom is the simpler model. The model that has more degrees of freedom is estimating fewer parameters. It's the simpler model.
okay, yeah, that was what I was.
So it's just like, just keep saying that to yourself a lot.
Okay.
Because I think sometimes that can be confusing, but just say like, hey, simpler model, fewer parameters, more degrees of freedom. And that model is going to have a higher chi-square. I mean, at best, it could be virtually identical, but so the model with the higher chi-square is going to, it's going to have fewer, it's going to have fewer estimated parameters, more degrees of freedom. And that's your simpler model. Yeah? Questions? Woo! We did it! Except for model fit, which we'll do next time. Yes?
Could you go over what the default are?
So, I mean, there are so many of them. So I can't possibly go over all of them, but the salient ones I will go over right now. The most important salient one is that if you have exogenous variables, by default, M+ will correlate them. That's why I didn't have some of those correlations in that measurement model, and it still was going to give me the same. I didn't, technically with my measurement model, I don't actually have to specify any correlations among exogenous variables, and they will still come out in the output. You can try it yourself at home and, confirm that that is true. So that's the important thing. Like, that's one of the most important defaults is that if you've got exogenous variables, it's going to correlate those exogenous variables by default. If you have endogenous variables, generally speaking, it won't correlate endogenous, which makes sense, right? That it won't do that by default. What other defaults? Oh, marker variable. That's the other big one. So you don't have to declare a marker variable, M+. If you're doing any kind of a measurement model, it will use the first variable after the by as your marker variable. Now, I was going to say, in the homework, I tell you which variable to use as a marker variable just to make our job easier to grade it, because as I said, the unstandardized estimates would be different if you use different marker variables, even though the model fit and the standardized estimates would be the same. So what that means is when you do your homework in M+, just make sure that whatever I said to be the marker variable, just make sure that's the first one you list after by. That's all you have to do. And that's a default as well. I think those are the only two big ones that are really, I mean, there are lots of other defaults, but those are the two big ones that are salient that we've talked about, I think. Are there any other ones that I'm not mentioning, Jocelyn, that I should be? That's it, right?
Yeah, you mentioned earlier with the endogenous, the disturbances. So being correlated.
Oh yeah. So that's not usually done by default, right? And then just to also to remember, this isn't a default, but just to remember that in M+, if the variable's exogenous, and you just like, if you just list, let's say it's variable 1, and it's exogenous, that variable 1 is it's going to be the variance of variable 1. But if it's endogenous, then the variance is actually the variance of the residual, right? If it's in a measurement model, then it's going to be the measurement error. And if it's in a structural model, it's going to be the disturbance variance. But just remember, it might look like it's referring to a variable variance, but if it's endogenous, it's always referring to a residual variance, not just like the whole variance. Oh, one last thing. Oh, it's 12:15. One last thing to say. So I did put up a couple of appendices from the book, one of which goes through the standardized tracing rules in a lot of detail. So I noticed that there were, I guess, some questions about that on the last homework. So, or problems, or however you want to think about it. So you might want to go through that appendix if you're still sort of struggling with that. And remember that the homework for today is not due until tomorrow at 5, which is good. And also remember that the homework for today, there's the first set of models, and then there's, you can, for the extra credit, I basically just ask you to kind of reverse the causal arrows, reverse the pathways, and run that model. And that's worth an extra 2 points so every homework is 6 points, which really is percentage points of your final grade. So 2 points might not sound like a lot, but if you get it right, that is 2% on your final grade. So for those of you who are like feeling like a little shaky after homework 2, my best advice to you is to make sure you do the extra credit, because that's like if you could, that's an extra 2 points right there on the final grade.
And there's an exam in number 7 for homework 4.
And yes, and you don't need to do number 7 for homework 4, which is the model fit. And we will talk about model fit next time. And that is it. Whew. Maybe we need like a 4-hour class. All right. Let's see. I need to stop this recording somehow. Stop. I can stop sharing. Stop recording. Stop. Okay.